In this demonstration of the Ext Chart program, we'll construct the May spectral sequence computing a slice of the atom Z2 page for the atom spectral sequence computing the homotopy of TMF, connected TMF. Ext Chart has built-in functionality for computing and constructing May spectral sequences like this one. This is, of course, something that you can coax the program into doing manually, but if you use the built-in features, then it's able to keep track of some extra structure. The dialog constructing such a spectral sequence takes two inputs. One is that it's some sort of truncation width, so the program can't compute out infinitely far. But if you tell it ahead of time that you want to consider the part of the spectral sequence living in the range s plus t minus s less than or equal to 20, then it's happy to do it for you. There's also this other field for dealing with certain pre-specified subalgebras of the full neuron algebra. If you fed it a 1, then you get a spectral sequence computing the atom Z2 page for the homotopy of real K theory. If you give it a 2, then you get the 1 for connected TMF. And if you uncheck the checkbox, then you get a spectral sequence computing the full atom Z2 page for the two-adic sphere. What the program first shows to you is just the E1 page of the atom spectral sequence, or of the May spectral sequence. So you can see that it introduces the correct generators, H0, H1, H2, and then H20, H21, H30. It also selects maximums to truncate it along this diagonal line. And more than that, it also understands the structure of the T1 differential. So all of these things are built in. If we pick a particular differential, you can ask it for its structure. The way that Ext Chart keeps track of differentials internally is as a sequence of potentially partially overlapping sub-definitions. So this is in general a list of possible definitions, and then the structure of this dialog box contains a description, the dimension of a subspace on which we're going to control the behavior of the differential, an inclusion describing what subspace in particular we're thinking about, and then the behavior of the differential in that subspace. So all in all, this dialog says that the May D1 differential applied to H30 has the behavior of sending H30 to H12, H20 plus H10, H21. If we flip to the second page, then you'll see that sort of from scratch, the program doesn't know anything about what happens on future pages. So it's able to compute the cohomology, and you see all these dots, but there ought to be more differentials here. The structure that allows the user to explore the structure of the May spectral sequence and further the computation is that of squaring operations in Nakamuras lemma. So if I pick a particular differential down here, so this is the class H20, and that's the differential sending H20 to the product H10, H11. Then I can apply Nakamuras lemma to this differential. Nakamuras lemma computes the standard squaring operations in the May spectral sequence, and then asserts that the differential intertwines with them appropriately. So for instance, here's square 0 applied to H20, you get H21. More interestingly, if you apply square 1 to it, then you get H20 squared. So I'm going to apply Nakamuras lemma to each of the differentials on the 1 line along square 1. When I turn the page, now Ext Chart knows about 3 differentials on this page. So this differential comes from the application of Nakamuras lemma, and it says that D2 applied to H20 squared is given by the sum H11 cubed plus H12 times H10 squared. Once you know about these 3 differentials, then Ext Chart is able to infer a whole network of them by applying the Leibniz rule. In order to apply the Leibniz rule, Ext Chart needs a little bit of help. You need to tell it where the indecomposable generators of the spectral sequence are. And here they are. So now Ext Chart knows about a variety of further differentials, and if you turn the page, much of the garbage that we saw disappears. On the other hand, this still isn't quite right. If you're familiar with this calculation, you can see that some things are still wrong. There ought to be a gap in here, etc. And the thing that's missing is that there ought to have been a differential here. These two dots are the first place where our computation differs from the real thing. And so how are we supposed to learn that a differential should have been placed here? Well, it turns out that this differential is forced by H0 divisibility. So let's have Ext Chart show to us the structure of H0 multiplication in this spectral sequence. So here I'm going to tell it to track H0 multiplication, and then I'm going to turn on the layer showing H0 towers. And now you can see something interesting. So we're interested in these dots right down here. This is a little messy, it's hard to see, but these up and left arrows are all the differentials that we used to be studying. And what you can see here is that there is a differential connecting these two dots, and these dots are connected to the ones beneath them by H0 multiplication. Differentials are H0 linear because the differential on H0 is 0. And so the only way that this differential could be non-zero is if the one below it were also non-zero. And so we're going to add a partial definition here. I'll leave myself a note. I learned about this thing by H0 divisibility. And I'll introduce the differential. So I had to know that what the cycle here was called. This is something that Ext Chart is also happy to tell you. It said that it was the sum of the two terms. And sure enough, if you highlight the term and ask for a homology representative, Ext Chart says that the homology representative here is given by the sum of these two things. Ext Chart is also happy to tell you about cycles and boundaries at a particular page. So this is the unique cycle, and there are no boundaries. Well, now that Ext Chart knows about this differential, we should remind it to propagate it through the spectral sequence using the Leibniz rule. So you can see that one or two new differentials appeared up here. And when we turn the page, we see something much more reasonable. So here's a pre-prepared computation of the spectral sequence. There. Out through degree 15. So you can see that all of the dots match up. This is a picture. This is Andre Enriquez's picture of the actual atom spectral sequence. So the differentials, the up and left arrows that you see in the top picture, are in fact atoms differentials, which is why we don't see them. But there are also the up and right labels, or arrow lines, which are supposed to describe various multiplicative structures. So for instance, the straight vertical ones, which we do have in our picture, are multiplication by H0. So in particular, you can see, for instance, here there's no line, but above it we have an H0 tower. But then there are also these lines denoting multiplication by eta, and these lines denoting multiplication by nu. We can add those to our spectral sequence just as we did before. I'll add a layer detecting eta, and another layer detecting mu, and then I'll enable both of those layers. There are the eta multiplications, and here are the nu multiplications. And so what you can see is that we've picked up all of the differential that Andre knew about, or all of the information that Andre knew about when he performed this computation. So again, in more complicated slots, positions, Ext Chart is still happy to tell you about exactly what classes live here. So by this page, in each position, there's only one homology class. But if you flip back to, here we are, to other positions, you can see that there's a complicated structure of what the subspaces of cycles and boundaries are at any particular position.